Hello. In 1983, cassette tapes finally overtook vinyl as the most popular form of recorded music sales format. And by 1989, when Billy Joel's Stormfront came out, cassette tapes were still number one, but it would be their last year, at still around 51% of the market, because CDs were starting to overtake them. Now in 83, CD sales were only about 1% of the market, but by the time these CDs came out in 97, they accounted for about 84%, eventually reaching 96% of the total market for music sales. And of course, these days, very few people buy CDs or cassette tapes. So how would we model something like that? It's certainly not a linear trend, but we still want to use the ideas of regression to find the best fit function. But we need to enlarge the types of functions we're allowed to use, and so we need to adapt our techniques. So that's what the topic for this section. And as far as CD sales, that's one of the exercises, so you can take a look at that after we've gone through some examples. So let's jump into our first type of function, and that's going to be a power function. So a power function is something of the form y equals a times x to the b, and we're going to assume x is positive. Now, let's try to use the same technique as we had before, where we want to minimize error. So we're given data of the form xi, yi, where I is between 1 and n, and recall that e is just the sum from I equals 1 to n of the actual value minus the model squared. And we want to minimize e. So it's still the sum of the squared error, but the problem is that if we try to use the same strategy as before, we run into a roadblock. Recall the strategy from before is use calculus. We want to take some derivatives and then set those equal to 0. So I need the partial of e with respect to a, because keep in mind, what's the goal? The goal is to minimize a, or minimize e, by finding the optimal a and b. So those are my two unknowns. So if I do my partial of e with respect to a, I still get my sum, bring down the 2, yi minus a xi to the b, and then multiply by negative xi to the b. Because a is the variable, so xi to the b is just a coefficient. And we want to set that equal to 0. Likewise, if I do the partial of e with respect to b, I'm going to get the sum, again, 2 yi minus axi to the b, because I'm using the power rule. And this time, b is the variable, and so I have axi to the b times the natural log of xi. And I'm still setting that equal to 0. And the problem is this is no longer a system of two linear equations and two unknowns. It's two equations, two unknowns, but because the b is in the exponent, there's no easy algebraic way to solve. And so that leaves us with a dilemma. How are we going to deal with that? So the idea that has been used historically is let's try to transform this to make it look like something we can solve or we already know how to do. And this is common in math. If you can't solve a problem, try to transform it into something that you do know how to solve and then transform it back when you're done. And the key to the transformation is to take the logarithm. And it doesn't matter what type, but we'll stick with natural logarithm for now. So we'll take the logarithm of both sides. We'll call this equation up here star. And so I have natural log of y equals the natural log of a times x to the b. And of course, the advantage of that, by properties of logarithms, is I can split up a product into a sum, and I can also bring the exponent down. So now what I have is the natural log of y is equal to b times the natural log of x plus the natural log of a. And notice, if I call this y capital Y, let's say, and call this X, then what I really have is capital Y equals bx plus natural log of a, and this is linear. And so now I can apply our regression techniques to this new set of data and solve for b and natural log of a. And once I know b and natural log of a, right, a slope and an intercept, then I can transform them back into a and b, which will solve the original problem. Now, there's one problem with this, and that is that when we minimize SSE, so if we want to minimize E for the new data, right? In other words, natural log of xi comma natural log of yi, this is not necessarily the same as minimizing E for the original data. So what minimizes E, or SSE, if we've used that term as well, for this transformed data is not the same as the original data, and so you could get a discrepancy, but it's the best we can do if we're going to use this calculus idea and what we already know about linear regression. So if it's a really good fit, that distinction is not going to matter too much, but as the model starts to lose some accuracy, then that difference could start to become significant, and we'll eventually see that as well. So that gives you the background. We will see this in action in an example in the next video. We'll see you there.